The meaning of Psi-squared. Psi-squared indicates the probability of locating a minute particle at a given point in space. A plot of Psi-squared for an electron in an atom over 3D space, it shows us a region of space where the probability of finding an electron is high. Now the appearance of Psi-squared plot shows that the electron is really spread out over a region of space over time. This actually leads to a useful interpretation, namely that the electron in an atom behaves like a cloud of charge. Thus we have, and this is really the modern model of the atom, the charge cloud model. It's a model that depicts the electron as a cloud of negative charge. Now the electron in an atom is depicted by a three-dimensional standing wave. For the hydrogen atom, or a hydrogen-like particle, and by that I mean a particle with a positively charged nucleus and only one electron outside it. For example, a helium plus one ion would be a hydrogen-like particle. It has a positive nucleus and one electron outside it. Anyway, for a hydrogen atom or hydrogen-like particle, application of the Schrödinger equation yields a set of waves and associated total energy values. When you solve the Schrödinger equation for the electron, it's a twofer. You really get two things. You get a mathematical description of the electron wave given by psi, and you also get the energy value for the electron in that given energy level. Wave functions can be expressed in Cartesian coordinates, that is, with x, y, and z coordinates, but it's actually more meaningful to express them in polar coordinates. All right, polar coordinates. When's the last time you did a plot in polar coordinates? It's an alternative coordinate system, and it is especially useful for plotting psi and psi-squared. There are three variables in polar coordinates: r, theta, and phi. R measures the distance of the electron from the nucleus. Theta is the angle that the R line makes with the z-axis. Now, customarily, we always write the three-coordinate axis, the z-axis vertical, and the x and y horizontal. The third third coordinate, phi, is the angle that a projection of the R line in the xy plane makes with the x-axis. So if we take the R line and we project that line in the xy plane, this projection line here, we then look at the angle that that line makes with the x-axis, and that is our phi angle. Now you can mathematically convert from Cartesian coordinates to polar coordinates. Mathematically, it's done as follows. X is expressed as r sine, oops, we've got the wrong font here. That's sine theta times cosine phi. Y is r times sine theta times sine phi. Z is r times the cosine of theta. Sorry about that. Those letters should be the Greek letters. A plot of y squared in coordinate in polar coordinates in 3D space gives a mapping of the electron density over 3D space. The value of psi square at any point in space within the atom can be interpreted in a couple of ways. One, the probability of finding the electron per unit volume at that point in space, or two, the electron density per unit volume at a point in space. An examination of the resulting psi functions, the solutions to the Schrödinger equation for an electron and a hydrogen atom, reveals that each psi can be written as a product of three functions. Now, that alone is not really obvious. When you discover that when you take a given psi function in its polar coordinates, and if you alter it and modify it mathematically, you can take this overall function and break it up into the product of three separate functions. A product of the function in terms of the variable r, a second function, a function in terms of the variable theta, and a third function in terms of the variable phi. So that's going to be significant for us. We're going to look at the three polar wave function components: the r function, the theta function, and the phi function. The r function is called the radial function. The theta and phi together are called angular functions. The product of the two angular functions is called the total angular part of the wave functions. It is the phi function times the theta function. Now, each component function can be graphed separately. There's also, we'll explain this more fully later, what's called a radial distribution function. It's the radial function squared multiplied by this mathematical parameter 4 pi r squared. R is remember, the radius. This function gives the probability of finding the electron at a given distance from the nucleus summed over all angles. This term for our 4 pi r squared is proportional to the volume of an infinitesimally thin shell with a radius r, and I'll explain this more fully in our next class. What arises naturally when you solve the Schrödinger equation and arrive at psi values and energy values, or psi functions and energy values, naturally are a set of parameters called quantum numbers. I'm sure you remember this from general chemistry. These quantum numbers are mathematical parameters which again rise naturally when you do the math, and their values are restricted to integer or whole number values. There are 4 quantum numbers altogether that emerge. The first quantum number, n, and that's the same n we saw with the Bohr model, where we use the n value to represent the energy levels of the electron in the atom. N equals 1, the lowest level, n equals 2 is the highest level. So that n value really is going to tell us the major energy level, or we also say shell, where we find the electron. The second and third quantum numbers are denoted as L and m sub L, respectively. There's a fourth quantum number that's denoted as m sub s, and it was actually added later as a relativistic correction. Well, we'll explain that in more detail later. Here's a chart that gives quantum numbers, the 4 quantum numbers. This is the name that's provided for them, their possible values, and the meaning. The first quantum number n, it is called the principal quantum number, and it has the integer values. The possible values are 1, 2, 3, 4, and so forth. The second quantum number, L, is called the orbital angular momentum quantum number. Qn is the abbreviation for a quantum number. Now its values, possible values, are different than the values for n. It can be a whole number, either 0, 1, 2, and so forth. Now there's an upper limit. In fact, the possible values of L depend on the value of n. It depends on the particular energy level that we're at. Because the values of the second quantum number L run from 0 all the way up to the maximum possibility of n minus 1, from 0 and 1, 2, and then the highest would be n minus 1. Physically, what does the L quantum number mean? It indicates the magnitude of the orbital angular momentum. It also indicates the shape or the number of lobes of an orbital. The third quantum number is m sub L, and it's called the magnetic quantum number. It has the possible values 0, plus or minus 1, plus or minus 2. The possible values of m sub L depend on the value of L that's in question. Anyway, this quantum number m sub L indicates the orientation of the angular momentum for a specified L value. It indicates the orientation of the orbital in space. The fourth quantum number, m sub S, is the spin magnetic quantum number. It has possible values plus 1/2 and minus 1/2. It turns out that the electron has a property of spin. It acts like a ball of charge that spins on an axis in two possible directions, clockwise or counterclockwise. Anyway, this quantum number specifies the direction of spin. Now, the possible values of L, if you come back to the second quantum number, 0, 1, 2, or 3, we'll also reference those by small case letters, S, P, D, and F. The particular value of L indicates, in fact, the type of orbital where the electron is found. If you have a value of L equals 0, then this would correspond to the S orbital. On a given energy shell, if the value of L happens to be 0, then this means that the electron would be in a p-type orbital. L equals 2 corresponds to a d orbital, and so forth. Some follow-up thoughts. We previously showed for the hydrogen atom that the energy of an electron at a given level, E sub n, can be calculated with a simple equation. This is the equation derived by Bohr, and it's often called the Bohr equation. En equals negative times the RH factor. Strictly speaking, that's related to a little different than what we called the Rydberg constant. So it's minus R sub H over n squared. Now, more generally, for any hydrogen-like particle, the equation is modified. In other words, if we had, let's say, a helium plus 1 ion or a lithium plus 2 ion, one electron around a positive nucleus. We modify this equation here by taking the equation and multiplying by the nuclear charge squared. That nuclear charge is given by the atomic number. That the symbol used for that is Z. So if we wanted to calculate the energy levels for a helium plus 1 ion, the charge of the helium plus 1 ion, the nuclear charge, is plus 2. The atomic number of helium, of course, also 2. So if we substitute the value 2 for Z in this expression, it tells us that we need to square that, Z squared, and then we multiply that of course would be 4, times this the quantity minus RH over n squared. And that would give us the energy values for energy levels in the helium plus 1 ion. Bohr also, we mentioned this before, derived equations for calculating the radius of his orbits. This equation shown here, in fact, is the equation that Bohr used to calculate the radius of the smallest orbit for at least his model of the hydrogen atom, the n equals 1 orbit. We call that the Bohr radius. Now, with respect to our modern picture, modern model of the atom, which is more of a diffuse electron cloud picture, I'm going to explain the significance of this Bohr radius in class later. But for now, here is the equation that allows us to calculate the value of the radius of the lowest n equals 1 orbit. It's given the symbol a sub naught, 4 pi times e naught h bar squared over me times e squared. M is the mass, e is the charge. The epsilon value is another quantity that I'll explain later. H bar is actually h over 2 pi. Anyway, when you plug in the values, the numerical value of the Bohr radius is in picometers, 52.9 picometers, 0.0529 nanometers. Now for a Schrödinger type hydrogen atom of the electron cloud picture, with respect to the s orbital, what's interesting here is that in the 1s orbital, the most probable distance of finding the electron in an atom, we call that R max, is in fact related to the Bohr radius. This R max equals the Bohr radius divided by the nuclear charge, by the atomic number. Now here's a table that, well, it's got a lot in it. This table lists the actual mathematical functions for the angular parts, both in polar and Cartesian coordinates. In class we'll go over this in more detail, but you can kind of just look and behold that for now. The next slide shows the mathematical forms of the radial functions, the capital R function, for the different possible orbitals, the 1s, 2s, 2p orbitals, and so forth. And we'll come back to this in class at a later time. This completes part 2 of the Introduction to Atomic Structure video. Goodbye.